and welcome to the doctoral meeting. I'm especially happy to be here because this activity shows that we keep on working in our usual tasks. And we are here to know more about the work that is being carried out by Fernando Estévez, a CITIUS PhD student. And he is working on an interesting problem related to machine learning. In particular, the relevance of machine learning and in particular deep learning is known by all of us because it's applied to a variety of environments. And in particular, he is interested in real-time learning problems and aggregating the learning provided from autonomous systems to generate global learning. She's going to present the work and the details. Fernando has 20 minutes to present the work, and at the end we will have time to ask some questions about the work. So Fernando, when you want.
Okay, thank you, Dora. Let me share the presentation. Can you see now the slides?
Yeah, perfect.
Yes.
Okay, so good morning, everyone. So the purpose of this presentation is, as Dora said, is to explain the main points addressed so far in my thesis, which deals with a new way for devices to learn in society and continuously. So what does this mean? Well, I will start with a bit of background to give you a context. So there's an increasing number of devices, of smart devices around us at our homes, companies, etc. Devices like smartphones and tablets, wearables, robots, and more. And we use them for many applications, in education, health, sport, leisure, etc. And most of these devices are already interconnected or connected to the cloud and can collect huge amounts of data from their environment. So this data is very useful for us because we can use it to train models that allow the devices to adapt and improve their behavior. So the question is, what's the best way to do this? And the truth is that different learning paradigms have emerged, and some of them are more popular than others. So the most common approach is the cloud-centric one. And using this approach, we collect the data in the devices and then move all the data to the cloud. And there in the cloud, a model is trained using all the data from all the devices using a dedicated computer, right? So, and finally, the model can be sent back to the devices to use it or not. It can remain also in the cloud. So, in the last decade, deep learning, as you know, has become the most popular way to learn these models from huge amounts of data in the cloud. So, regarding the performance of these kind of models, there's no doubt about their possibilities and potential. However, when it comes to the scenario of distributed devices, such as smartphones or robots, this can be very inefficient or even invisible because, especially when we talk about a large number of devices or users, we have to address some challenges. And the first one is the scalability. And in terms of storage costs, communication costs, and computational costs. But we have also to take into account other issues such as data privacy and sensitivity. Because in recent years, governments have been implementing more and more data privacy legislations in order to protect the consumer. So nowadays, it is not as simple as sending all raw data to the from the devices to the cloud, which is okay, but we need to know how to deal with it. And there are even more restrictions, such as non-stationarity of data, that I will explain later. So on the totally opposite side, we have another paradigm, which is distributed learning. And following this approach, the learning process is carried out in a distributed and parallel manner on the devices themselves. And then, each device performs a local learning in a synchronous way, and normally there is a global integration stage later in the cloud, so that a final model is consensuated. So this sounds more scalable and appropriate for the context of devices. And moreover, it makes it easier to protect the privacy of the users, because there's no need to share raw data with the cloud. And very close to distributed learning, we also have federated learning, which was proposed by Google in 2016. And the main difference between both, between federated and distributed learning, is that distributed learning mainly focuses on parallelizing computing power, and federated learning is more focused on data privacy and training on heterogeneous datasets. Okay, distributed and federated learning are much more suitable for the context of devices than centralized learning. However, there are still some challenges that these approaches do not address or only partially address. And the most important is non-stationarity. And now I'm going to explain it a bit. So most machine learning algorithms assume that data comes from a static distribution. But in most real-world situations, the data distribution changes over time. And I will talk a little bit more about this issue later, but for now, I can tell you that in order to deal with this problem, there is another framework called continual learning. But in the end, what happens is that each proposal, each approach focuses on a specific subproblem and normally neglects others. So, for example, in the case of continual learning, we focus on non-stationarity of data, but it doesn't care about data privacy, for example. So we have developed a new paradigm called glocal learning with the aim of facing all the challenges we have mentioned so far. And as you can guess from the diagram, our proposal shares ideas or has similarities with other paradigms, but at the same time, it cannot directly fit into any of them. So what is this glocal learning about? Well, glocal learning is a continual learning process that works in a distributed manner at two different levels, locally in the devices, but also globally in the cloud. And that's why we call it glocal, from local plus global. So the main actors here are the devices, not the cloud. This is an asynchronous process, not synchronous, and each of the devices creates and refines its own local model of the problem. And for that, they must continuously acquire new data using their sensors. When a local model is obtained, it is sent to the cloud, and there a new learning stage is performed to join the models from each of the devices. And thus we obtain a global model, and this is the global learning stage. So the global model is then shared with all the devices in the network, and thus each device can use this global model to make predictions that will be more accurate. So this process is repeated over time, and note that no raw data is sent to the cloud at any time, only models, so user privacy is preserved. I have to say that at least for now, our work is limited to supervised and semi-supervised problems, and in particular for classification tasks. Okay, so that was an overview, and now I'd like to delve a little into the details. And I will start by talking about the global learning stage. We have the local and the global stage. I will start with the global stage. So all the devices train their own local models, and we'll see how they do this later. But for now, it's enough to know that each device trains locally a model, and eventually these models are sent to the cloud. So in the cloud, we have to join, to merge in some way the local knowledge of all the devices. But how? This is something that federated learning also deals with. And in the case of federated learning, there is only one single model, which is a deep learning model, a neural network, which is shared with all the devices. And each device locally modify the weights of the neural network. And then in the cloud, we average these weights. But remember that in our proposal, each device learns its own local model independently from the others. And we don't want to be tied to a specific type of learner, like a neural network. We want to train the most suitable learner for the task, or the one we like the most, whatever. So we could even perform training using a different algorithm on each device. For example, on one device a support vector machine, and another a random forest. So our approach is pretty simple, and it is this one. We send the local models to the cloud, and then they are joined using a rule-based ensemble. And in particular, we use a product rule to obtain a single prediction. However, this is not scalable because if we put all the local models in the global ensemble, we could have thousands or millions of devices connected, and some of them will learn the task better than others. So the solution we propose is to select only some local models to participate in the ensemble. And we propose a selection method based on a ranking, which we call distribute effective voting. There's no time to go into the details, but basically what we do is to rate each local model with a score. And in order to calculate that score, each local model is evaluated by other devices using their own local data. Okay, so those are the main elements of learning at the global level. And now we should talk a little bit about how do we learn each local model on each device. So we could simply gather certain amount of data and then train a classifier. As I said before, for example, a support vector machine, a random forest. In some cases, it could be even possible to train a deep learning model, like a convolutional neural network, whatever. So we train a model and send it to the cloud. And we could stop there. But that is a very naive approach because we are not facing the problem of non-stationarity. So talking about non-stationarity, I'd like to explain a little bit more about this, to explain just some important concepts. So the thing is that most machine learning algorithms work under the assumption that data comes from a static distribution. But this assumption isn't true in many real-world applications. And normally the data distribution changes over time. And this is what is known as concept drift. So if we train a model now, maybe in 1 month or 1 week or even 1 day, it is useless because data is continually changing. So what do we do instead? Well, we propose to do all this, and this is the continual local learning workflow for each of the devices. Each device collects data over time, and this raw data is pre-processed to extract patterns. If we work in a semi-supervised context, then we will have labeled and unlabeled patterns. So what we do with unlabeled data? We perform a semi-supervised data labeling stage, and we don't have time to delve into details because it is not so important, but basically we use a method similar to self-training, and we use the global model that we get from the cloud to predict the label of each unlabeled pattern, and then we filter the predictions based on their degree of confidence. If the confidence is high, then the prediction is accepted. Okay. We collect data, and the collected data is stored in the local memory of the device until there is enough data to train a model. Question: how much data is necessary to train a model? Well, the answer is not simple because it will depend on many factors, such as the complexity of the problem, the chosen algorithm to train the model, etc. But so what we do is to define a minimum amount of labeled data from each of the possible classes, looking for a balance in the dataset. And once we have enough data, we train a first local model. And once the first model is obtained, it is sent to the cloud. Okay, so now model trained, but as I said before, if a concept drift happens, the model will lower its performance. So we need to detect when a concept drift happens in order to somehow update the local model. And for that, we use a drift detection technique. And there are several ways to do this that we can classify in 3 main categories: error rate based methods, data distribution based methods, and multiple hypothesis test methods. And in particular, we use a distribution based method, which is an adaptation of the original method proposed in this paper here on the bottom. And this method has the advantage that we don't need to know the actual data labels to detect the drift. Basically, what we do is to compare the probability density functions of 2 beta distributions, one with the most recent data and one with the oldest data in a sliding window. And the beta distribution estimates the distribution of the confidence of the local classifier. And if the two distributions are too different, we consider that a drift has occurred. Anyway, if a drift occurs, if a drift is detected, then the local model can be updated. And there are several approaches to do this, and we have implemented and tested some of them. And the simplest one is simply get rid of the old model and train a new model from scratch. But as you can imagine, this is not ideal. So a better option is to train a new model on the new data and add this new model to a local ensemble with the old ones. So in the ensemble, you can keep a limited number of recent models, for example, 5. And in some cases, for some learners, such as neural networks or some boosting methods, you can also train a partial model and resume the training later. So the ensemble approach is perhaps the most scalable one because you can use it with every base classifier you want to use. And every time the local model is updated, it is sent to the cloud again, and the global model is updated too. So this was all the theory, but now I'm going to show you some experimental results. So the task we are using to test our proposal is human activity recognition using the smartphone of the users. And we want to recognize activities like walking, standing, going upstairs, downstairs, running, sitting, or biking. And in particular, I'm going to show you some experimental results obtained using a dataset that contains data from 10 different users performing these 7 different activities that I have mentioned. And the smartphone plays in 5 different locations, these 5. So just to have a baseline, this is the best accuracy we are able to obtain applying some of the most popular classification methods like XGBoost or a CNN. And as you can see, we get around 90% accuracy in the best cases. And this is the first approach we mentioned at the beginning, the cloud-centric approach. So this implies sending all the data from the devices to the cloud. But now let's move to a more realistic context. And here we have a glocal learning process. So in the first plot, in the top, we can see the accuracy of each local model on each device. So each of the colored lines are the accuracies over time of each of the local models. And the thick black line here is the accuracy of the global model, which we obtain when combining the local models. Note that the global model outperforms all the local models. And in fact, we have pretty good accuracies practically from the beginning of the process. Well, this is not so important, but just to clarify, the plot in the middle shows at what time each local device is acquiring data and at what time it trains a local model. And the plot in the bottom is the amount of data is stored in each of the devices over time. So that was a very idyllic situation because all the local models performed pretty well. But one interesting thing is that if some of the users perform worse than others, it doesn't matter because in the global learning stage, we perform a selection of the models that are going to participate in the ensemble. So in this case, as you can see, it's the same dataset as before, but for the local learners, the light blue, the yellow, the pink, and the dark blue were modified because we introduce noise in their data. So these 4 learners perform worse than the others. But the global model still achieves the same accuracy, or more or less the same as before. And this doesn't happen if we train a traditional cloud-centric model. And in fact, here you have the results using the cloud-centric approach. And as you can see, all the methods lower their performances. This one is missing because I had no time to get the result for the CNN, so sorry, but well. And finally, in this example, we can see a much more realistic scenario because here we don't assume that data has to follow the same static distribution over time. The distribution can change. So in this case, data distribution changed 4 times. So 4 different concept drifts happen. Here is 1, 2, 3, and 4. So we can see how the performance of the global model is low at the beginning, because we are testing all the during the whole process. The whole process we are testing using the entire testing set. But at the end, the global model gives good performance. And this is good because we can see that it is able to adapt to all these 4 changes, learning the new concepts, but also without forgetting the previous ones. Okay, so to finish this section, I would like to take this opportunity to comment that the complete glocal architecture is already implemented to work on Android devices. And in fact, we have developed a demo application for the recognition of human activity that you can already try. Actually, we'd like to have your collaboration for future experiments when we get back to normal. So now, to conclude the presentation, I just want to finish with some ideas for future work. So we believe that we have opened a promising line of research, and we know that there is still a lot of work to do. So here I put some of our ideas. For example, explore optimal ways to combine knowledge locally and also in the cloud, study effective ways to perform local feature selection, analyze the use of the global model for instance selection in the local devices, the application of techniques such as amending for semi-supervised labeling and rectification, and finally, the possibility of adapt the local the global model to specific groups of devices or users that share similar properties. And that's all. Thank you so much for your attention. And now, if you have any questions, go ahead. Dora, I can hear you.
Perfect. The microphone. I'm not used to, even after 2 months, to use all the technical aspects. Well, thank you for your presentation. It was very clear. I have some questions, but I like to give the word to any person that want to make questions. Please, if you can ask for your turn using the chat, it's the best option. So if anybody has any question, please, you can write in the chat. While we are waiting, I'm going to make a question.
Okay.
This is a very interesting work, but there are many open issues related to your work, because you have to study. Well, you made a very good presentation, so you already detailed that it's important to know how to assemble the different methods, or how to combine the different models obtained in each one of the devices. You have to study the best option to select the relevant data in the different devices. You have to update the model with new information. The data is changing over time, so you have many issues to take care of. My question is, until now, what are the main issues that you are working on until now?
Okay, so what we do from the beginning was to define like several modules that we want to have in our architecture, and now our aim is to just work in each of the models independently. And we have a first proposal for each one, but now we can focus on several of them, and we are now working on how to improve both the local learning and the global consensus. So, for example, in the local learning stage, we have much work to do because there are a lot of methods for continual learning. So in fact, federated learning can also fit with our proposal. So we are exploring one way to let me show you here. So this is slide. So the thing of adaptation. So several approaches are valid, but some of them are better than others. So we are trying all of them, and we want to define for example, for a CNN with method we can apply, for a XGBoost, which is the better option. So that kind of stuff. And in the global stage, it's the same. We have to know or to investigate the best way to merge the knowledge of all the local devices.
But in my opinion, there are too many open paths in the work.
Yes,
because
yes.
The answer to many of these questions, from my point of view, depend on the problem that you are studying.
Mm-hmm.
Not only, well, if you select classification, as in your case, for example, the amount of data necessary to obtain a model heavily depends on the classification problem. So wouldn't it better to focus in only one particular problem, because in your work there are too many open issues?
In fact, we are focused on in some way on some particular problems, because we are only working with the task of human activity recognition. So it's a very specific task, and in particular we are focusing on semi-supervised classification, because generalize the semi-supervised thing to a fully supervised problem is straightforward. So that's where we are focused, and then we some of the modules of our architecture are now totally totally done. We don't, for example, the drift detection method, it's okay, it works okay, so we don't want to touch it for now. So we focus on that, human activity recognition. We focus on a specific type of device, which is the smartphone, and okay, if in the future we have time, we can use robots or whatever, but for now this is the task, and just
because I'm afraid that the answer to some questions, for example, the adequate method for combining different local models, could depend on the method selected for classification. For example, if you had a CNN, or if you have SVM, or
yes, in fact, for example, okay, so we have one implementation of this glocal learning is very general. It can fit with every classifier, because in the one I mentioned, the ensemble at the global stage, it can fit with any kind of classifier. In fact, you can have a different classifier in each of the local devices. And in the local stage, the adaptation method, if you use another ensemble for that is, you have one classifier, a drift happens, and you train another local model. So you have now a local ensemble of two classifiers. So that is totally independent from the method, the algorithm you are using. But this doesn't mean that it is the best or the most accurate approach. So, for example, this can work for all the algorithms, but maybe for a XGBoost, it is better to train a XGBoost model incrementally and not use an ensemble.
I understand. Alonso has Jose Maria Alonso has some questions, so please, Jose Maria, make the questions using the microphone.
I can read it.
If you can.
So Jose Maria is asking, how are you measuring the ground truth for evaluation, and how many samples are associated with each specific activity? Okay, so in this data set, this is a totally balanced data set. So we have this amount of label samples. This, in particular, this is a totally supervised data set. But for the experiments, it doesn't matter, because if we want to use a semi-supervised context, we just remove some labels and that's all. But we have the same amount of data for each of the users and for each of the positions and for each of the activities. So it's totally balanced. And the metrics, the ground truth. Okay, these models are trained. We try to do our best. So this is the typically process of data science. We did we try to obtain the most accurate models using the traditional approach. And in this case, what we do is to evaluate at each time we evaluate all the models using a whole testing set. That is, so if we have 10 users, we reserve 3 of them for testing, and the other 7 participate in training. I don't know if I'm answering the question, Gemma.
Please, sorry, Fernando, please, I would like to hear the questions, if it's possible, because it's not very...
Can you listen to me?
Yeah, perfectly. Thank you. Thank you, Jose Maria.
Fernando, the point is that I was also working with human activity recognition, and I agree that one of the main problems is that there is something that is continuous. It's not static. And when we are considering all machine learning classifiers, they are usually considered a static picture of the problem. So there are no movement in the data. And the point is that if you have a model, and according with your explanation, everything can be learned in time, progressively, the point is that I am not able to see really the ground truth for doing the evaluation, in the sense that if I'm doing a test, I have the phone. The phone has accelerometers, it's taking many raw data and so on. This information has to be processed some way, and I need to know which is the window of time that I'm considering for the period of time that I'm walking, or I'm not moving at all, or I'm running. So how to know? I guess this is what you call pre-processing stage. That is the first step. When you take data, then you pre-process of this information, and you are ready to send information for the classifiers. And these static classifiers are doing some classification that you are later merging in order to have this global view. But usually one really strong problem is how to identify the ground truth. This is a problem with robotics. It's a problem also in this kind of a scenario. Because if I want to test and I have someone who has the mobile phone and is moving freely, going upstairs, downstairs, you need to have some kind of record of activities of this person, in order that later, when you are looking to all the data, you know, from this time to this time, the person was walking. From this time to this time, was going upstairs. Then was running. And then you can compare and try to see if your algorithm was able to recognize properly all of this.
Yeah, I understand. So two things. Regarding the pre-processing, what we've done here is just apply the standard pre-processing that all the literature about human activity recognition propose, such a certain size for the sliding window, and some of the most relevant features. In the case of the traditional learners, like a support vector machine or XGBoost, and for the case of the CNN, you don't have to extract features because it is deep learning. So the pre-processing stage is just based on the literature. And regarding the ground truth, Well, obviously in this dataset that I've showed you, it is all labeled. But this is not realistic. But in fact, the guys that
But you were using the data that was provided by these people in the
these people label all the data manually, I think. But what we propose is, in fact, we have it here. What we propose is a collaborative system in which each of the users that use the application is responsible for label certain amount of data, and you don't have to label all the data that you are recording, but maybe you label some patterns, and there are 15 more users connected, and they label some other patterns, and at the end you have a semi-supervised context in which, joining the label data of all these users, you are able to train a model, or you are able to train a set of weak learners that when you merge in the global stage, it will perform better. And also the global model will help you to label data then. So that's...
So you expect that the users are just labeling the activities that they are doing to contribute to help you to learn the model using this kind of app, and say, in the last minutes I was walking, in the last 3 minutes I was going up there, for instance, sending information.
Not a very exhaustive labeling, but yes, they have to collaborate. That is the assumption.
But this is information that you can use for starting the learning of your model or creating an initial model. But so I understood that the idea is that even when the application is working, you are able to readapt the model, not necessarily asking the user to labeling all these activities.
So the model itself is the one that detects that a drift happened, because okay, we measure the confidence of the model when predicting new instances. So the model itself realized that a concept drift happens, but the users have to participate too. And this is an assumption that we have to do. In this case, for example, there is no reward. Well, maybe this application, well, you can give to the user a daily summary of the activities that they've done, or something like that. But this is something that, for example, Google also do, and they apply in the federated learning system. They apply this method to the keyboard, the keyboard of the phone, in order to predict the next words the user is writing. So their proposal is that the users that collaborate labeling data can access a improved version of the keyboard. I don't know if I'm explaining properly.
Yeah, there is a strategy in order to engage the users and make them to collaborate, because you need the more users are collaborating, the better data you can have and the better models you can learn. But anyway, in case that there are no users collaborating, but you already have the beginnings and collaboration by a small group of users, you can learn this initial model. And then the interesting point is this idea of concept drift, that you are able, even without having feedback for new users, but you are able to some way adapt the information in accordance with the new activities that you are detecting. When you detect that there is a change in the activity, I guess this is the concept drift.
And another interesting thing is that this is an asynchronous process, so anybody can join this process of learning at any time. So maybe you join or you install the application just in the middle of the learning process, and you receive automatically you receive a model from the cloud that is trained, and you can use it from the beginning without labeling any data. So,
do you have any paper written explaining this a bit more in detail? Not yet.
Yes,
I'm
but
especially interested in the way how you are identifying the importance of the different models in order to do the selection in the ensemble. Because at the end, I think this is really important. It has a lot of impact because you are telling, okay, I have 200 people contributing, but I know that there are 10 who are the best one. And these 10 are contributing to my model, because if I introduce the others, then I'm introducing noise and I'm destroying my model instead of improving it. So how to identify the weights of each of the models and how to know which models are better or worse in order to contribute to the global model, this I think is very, very important, and it has a lot of impact in your result.
Yes, now we assume that each local model has the same weight, but not all the models, all the local models participate. So we select, what we do is we cannot send data to the cloud, but from the cloud you can download models. So what we do is from the cloud we ask some random users to evaluate the models of other users. At the end, each local model has a punctuation based on a series of accuracies, of distributed accuracies from other users in the network. So we are able to know which models are better than others.
Well, excuse me, because Roberto wanted to make some contribution to the discussion, because Roberto, are you?
Yes, I am. Thank you very much. I just wanted to say 2 comments regarding what Jose Maria was saying, although it's a little behind, regarding the ground truth. We use the 2 strategies you were just mentioning. One is working with labeled data. In the case of labeled data, we assume that the labels are correct, and we still can check. Basically, we feed our system with that labeled data, but in following a procedure that we can simulate a continuous learning. We don't provide the system with all the data at the same time. We feed the system with the data in different stages, simulating a continuous procedure, and we can still analyze whether the concept drift works, because, for example, Fernando didn't point it out before, but that data has been collected using the mobile in different positions. For example, when you have the mobile in the pocket, in the hand, in the arm, and so on. So basically, a change, even if you are trying to detect the same behavior, but with the mobile in a different position, that change of position is a concept drift, and we can check how our system detects that drift, basically. This application allows to analyze our system for real in a continuous learning. In this case, the ground truth is not trustable, in the sense that even the user can put wrong labels, for example, or doesn't collaborate much, and so on. Basically, the idea is that, and here is when we have to work with the semi-supervised strategy. And in this case, the global model is really relevant, because basically when the user is not labeling, you get data, but you don't know the task the user is doing. So basically, with the global model, you can label that unlabeled data and so on. This is a normal strategy. And also the user, if he is not happy with the behavior or with the accuracy of the global model, can change can start labeling. That's another possibility, and so on. But the ground truth with this application is not so easy. Basically, only when we use it, we can check whether whether the model is working fine or not. But I mean, Fernando, the researchers, basically, when we use the application, we can be more specific or more accurate, but the normal users sometimes label properly, sometimes don't. And regarding what Dora said at the beginning, I would like to point out that we agree with her in the sense that there is no unique solution for every possible classifier. In the sense that, yes, glocal learning, the way you apply, for example, glocal learning when you work with CNN or when you work with random forest or when you work with stream boosting and so on, the solution is not the same. So basically it's like right now, before trying to achieve unique formulation, basically what we are trying to do is to extend the different the different strategies, the different algorithms. We are trying to extend them to a glocal environment, a glocal framework. So basically we have like a framework, blocks basically, but we have to achieve or to extend the application, the different strategies. We have to extend them to this glocal environment, and then after doing this is when we can maybe try to reach some kind of global formulation, but probably the solution cannot be unique. It depends on the learning strategy you are applying. For example, after you detect a drift, if you are using stream boosting, the solution or what you have to do after you detect a drift is different if you are working with stream boosting than with support vector machines, for example. So right now, we don't have a unique solution for all the learning strategies.
Thank you, Roberto. Please, Daniel had a question too. Please, Daniel, could you make your question, because it's easier than read the questions if you have the opportunity.
Can you hear me?
Yeah, of course.
Yeah, cool. Hello, Fernando. I was just curious about the type of data that is sent from the devices to the cloud. I mean, you have said that this data is processed somehow, so the privacy is preserved, but how is this data processed? What are you sending to the cloud?
Just the model itself. No data. I mean, it's just the model trained, and whatever it's codified, and just you send the model. Obviously, it will depend on the type of learners used, because if you use a KNN, that is the K nearest neighbors, it is the model itself. It's a series of patterns. So there can be sensitive data. So you have to take into account that in order to send a model. But that's all. It's only the model.
So the data gathered by the devices are processed in the device.
Just in the device, and keeps in the device, and then it's removed from the device.
And how? I mean, do you need a lot of performance in the device to generate this model, or is a simple task that every phone can do?
It's a simple task because specifically we are more focused on using traditional methods. Or for example, something like XGBoost, that it's very fast and very cheap regarding computational requirements. So you don't have to worry about that. If you use a CNN or something like that, maybe, but Google is using that in their devices. So, and in fact, you can also add, if that is a problem, you can add restrictions for the training, because this doesn't have to be a very quick process. It can take days, weeks, months, whatever. So you can restrict the training on the device, for example. So you don't train a model unless the device is connected to a power supply, for example, or connected to a Wi-Fi network, for example.
Okay, I see. Thank you.
Thank you very much, Daniel. Lorenzo had another question. Please, Lorenzo. If the question is not answered yet, I don't know if he's connected. If he's not here, we go to Alejandro. Alejandro, please, you had a question.
Yeah, most questions were related. I think they were answered.
Sorry, Alejandro, because we are listening to very bad. So could you make the question again? Alejandro, we didn't listen.
Yeah, it's in Alejandro was down with the connection. But anyway, he told that most of the questions were already answered. So.
It was related to the data set used, but I'm not sure. If he connects again, we can continue with the question. But in another case, we go to Nicolas, who has also a question. Nicolas, if you want to ask. Well, so we can.
It says that it doesn't have a microphone.
Well, so we can read we can see the question in the chat. He's curious about the process of sending back the global model to the local devices. I suppose says that the global ensemble model trained in the cloud weighs much more than every local model, as it contains each local model. Will the local devices be able of managing that amount of data? Thank you very much. So the problem is how to send the model again to the local devices, how to deal with this situation.
That's something we have to still measure in some way, because now we are working with a relatively small data set, and we only have 10 users in this case, for example. So if you only have 10 users and you reserve 3 for testing purposes, at the end, when you select models in the global stage, you have an ensemble of 4 or 5 models. So 5 models is not a lot, but obviously if you have thousands or millions, maybe selecting only 5 or 10 models is not the best option. So we have to measure this issue in some way. But for now, I can't answer properly. But anyway, the main rule is that obviously the ensemble has to weight less than the raw data. So that's all that I can tell you, Nicolas.
Well, I don't know if there is any other question.
Hi, hello, Dora. It's Paula.
Thank you, Paula.
Hi, hello. Well, I don't really have a question. I would just like to thank Fernando for his very good presentation. I think he did very clearly and really on time. So I think it was a very good presentation. And as Dora said at the beginning of the meeting, I am very happy that this event is taking place because, well, it shows that we are still working, and even if we are more or less enforced to do it remotely, we can see each other, even if it's only virtually, and I think this is good, and I would really like to thank you all for this. That's all.
Thank you, Paula. Thank you very much, Fernando, because the presentation was very good, and you are very good answering our questions. Your work is very interesting, as you had seen, because we had many questions. So thank you very much, and good luck with the work. And we can close the work here if you have any comment.
No, it's all. Thank you.
Perfect. So we can finish here, and thank you everybody for being here. Goodbye.
Okay. Bye bye.
Bye.
Bye. Thank you.